Morning, students. We will go to the next lesson of your analog circuit. In our last lesson, what we have learned is the bias stability. We have seen that the biasing, that is the value of ICQ, that means the DC condition I collector current, which is extremely important for the function, or proper function of your transistor amplifier or any other circuit. Uh, It depends upon the environmental temperature. It depends upon the VBE, that means transistor base emitter junction voltage. It depends upon ICBO, that is transistor collector base reverse current. And also it depends upon the beta, the small signal gain of the transistor. Now, this dependency gives us a lot of practical problems. We have seen some analytical deduction of what are the various instability causes and what are those instability factors. We are going to learn those instabilities can be compensated for. So here we first go for a single diode compensation. The circuit is like this, Here the quiescent base current is supplied by a current source, IBB. Now, mind it, current source is not very commonly available. But anyway, this design based on the current source, IBB, and a diode is connected here through a resistor. This current flows here. A quiescent base current IBQ is supplied by a constant current source IBB. A diode D is so chosen that its temperature characteristics matches with that of the base emitter junction. So you have chosen the transistor. You know it is a silicon or germanium. You know it is base emitter junction characteristics. And you find out from your stock an exactly similar diode having exactly similar temperature dependence characteristics of the base emitter junction voltage. Now, how it works, suppose we have seen earlier that when the temperature rises, this VBE junction voltage drops. So, if VBE drops due to rise in temperature, then what happens? IBQ, if VBE drops, this IBQ will tends to rise because there is there's a resistance to this path decreases, so VB drops, those IBQ will tends to rise. But at the same time, the VD also drops. Now mind it, this IBQ is supplying current to two parallel paths. One is to this path and another is to this path, right? So if this potential also drops, so there will be a larger current flowing through this line. As a result, there will be a smaller current flowing through this line, right? As a result, the share of current between ID and IBQ remains constant. So this is a simple mechanism to compensate for the effect of change of VBE due to temperature. Now, if you want numerical equation, IB ID plus IBQ, right? Which is almost equal to IBQ, we take IEQ by beta, right? So, therefore, IBB into, we multiply both sides by RD, this resistance. IBB RD is equal to ID RD plus IEQ RD by beta. This is equation 1. Further, we go for voltage loop equation. This VD plus ID RD. the total potential drop in this line must be equal to total potential drop in this line. This is VBE plus IEQ RE. You agree? So IDRD is equal to, bring the VD on this side. IDRD is equal to IEQ RE, since VD and VBE are same. We have chosen a diode so that its junction voltage is exactly equal to VBE. So IDRD equal to IEQ RE. If that is so, then we combine equation 1 and equation 2. What do we find? IDRD, this is IDRD, and this is also IDRD. So what we get? IEQ RE is equal to IDRD. And IDRD from this equation is IBBRD minus IEQ RD by beta. Right? So, and minus IEQ RD by beta. So from here we get IEQ is equal to, divide both sides by RE, IEQ multiplied by RE, this IEQ and this IEQ goes left hand side. So this becomes IEQ into RE plus RD by beta is equal to IRD. Fine. This indicates that though the bias is independent of VBE, so in our first paragraph we have seen biasing is independent of VBE, but it is dependent on beta, right? And it will become practically independent of beta. RE is much, much more than RD by beta. Also, in that case, forward current through the diode may be too high. If you make RD very small, you have to make RD small, then there will be too much of forward current through this diode, right? So for all practical purposes, once again, 1:10 relation has been decided. RE much, much more than RD by beta, but we have taken RD is equal to 10 RD by beta. Once again, we land up in the same equation that we have decided earlier. RD is equal to beta RE by 10. If you maintain this relation, then what will happen? This system will compensate for the instability due to VBE. Also, it will compensate for the instability due to beta. So this was single diode compensation. Next is this single diode compensation continues. Now, this current source we have to avoid because current source is not very easily available or popular and designing a current source is also pretty difficult. So this current source, a separate constant current source, it can be replaced. Thevenin equivalent is VBB plus RB, a resistor in series, right? That you have, I think you have learned it in your school even, that this current source can be replaced by equivalent voltage source and source resistance RB. So that IBB, this current, is now equal to, this was the current IBB, this current is now VBB divided by RB plus RD, and this RB plus RD and RE in parallel. But RE should be multiplied by beta if you reflect it in the input side. I think this technique also you have learned in your first year device subject, that instance which is carrying emitter current, which is beta times the base current. So obviously, as an equivalent, if you reflect this resistance in the input circuit, it has to be RE should be replaced by beta RE, right? So this resistance in this path is RB plus sign here, RD plus beta RD and beta RE in parallel. Now we find IBB should be independent of RD or RE. This current IB should be independent of this resistance or this resistance, right? Now, for making that independence, this can be achieved if RB is much, much more than these two, right? In practice, it is enough to make RB in 10 times of this parallel factor. So RB is equal to 10, and when you make parallel of these two, it becomes RD beta RE by RD plus beta RE. Using this relation, using the earlier relation, RD is equal to beta RE by 10 that we have decided in just earlier page, we find now RB is equal to 10 multiplied by RD multiplied by beta RE is 10 RD. So finally we will end up with RB is approximately 10 RD. So this is a resistance you have connected in series with the diode, right? Now you have to decide what should be this resistance in your design parameters. This equation says if you maintain this resistance RB is 10 times this resistance RD, then your design is successful. Next type of compensation is by diode in the emitter circuit. There is a diode here, but mind that this diode is in the reverse direction. And the diode is in the reverse direction for so far as IEQ is concerned. But the diode is kept forward biased by a negative supply here through RD. And of current keeps on flowing through the diode through this negative bias. Now, how does it work? So it is current limiting resistance RD anyway. Applying Kirchhoff's voltage law in the base emitter loop, we find VBB is equal to IBQ RB plus this potential drop VBE plus IEQ RE minus VD, because this diode is chosen to be exactly same as this base emitter junction, minus VD. So from here you get VBB, VB goes to the left-hand side, VD also goes to the left-hand side. So VBB minus VEB plus VD is equal to IBQ RD plus IEQ RE. Now IBQ is approximately ICQ by beta. So ICQ by beta RB plus IEQ RE. And so from here, this IEQ is replaced by ICQ, which is 99.9% same value. So this becomes ICQ by beta multiplied by RB plus beta RE, right? So ICQ is equal to beta multiplied by this left-hand side, VBB minus VBE plus VD divided by RB plus beta RE. Since VBB, VBE and VD are same, because this diode has been chosen to be exactly similar as the base emitter junction. So ICQ is equal to beta multiplied by VBB divided by RB plus beta RE. So now ICQ becomes independent of VBE. So we have learned two methods how to make ICQ independent of VBE. Third method, diode ICBO in a germanium BJT. This is a diode here. In case of germanium transistors, change in ICBO is very prominent. That is a property of germanium transistors, right? ICBO, dependency of ICBO on temperature is very prominent. So, germanium diode of exactly same properties are kept in reverse bias here, right? Reverse bias, ICBO equal to ID at all temperatures. This ICBO, right? This reverse bias, reverse current goes through this reverse diode. ICBO is through ID at all temperatures. IB, this base current, is I1, this current, minus ID. This current I1 coming in, it gets two branch. One is IB, one is ID. So IB is equal to I1 minus ID. And I1 is equal to, this current is equal to, go to this loop here, is V, what is this current? Is VCC minus VBE, because emitter is connected to common. So VCC minus VBE divided by R1, this is I1. And this I1, we see, is I1 is a constant. It doesn't depend upon ICBO. I1 is a constant. So this I1 is a constant. If ICBO, what happens? If ICBO increases due to rise in temperature, it increases ICQ, because ICQ is equal to beta IB plus ICBO. It increases ICQ. But at the same time, ID also increases. If ID increases, IB decreases. If coming to this relation, this current is constant. This is the constant current. This current here is equal to VCC minus VBE divided by R1. I1 is constant. This is the constant current, no change. And this current has two branches, one branch here, one branch here, right? So if ID decreases, then IB increases. It has to increase. If IB increases, it in turn increases ICQ, right? That means if due to temperature, ICBO increases and tries to, ICBO increases due to rise in temperature, it tries to increase ICQ. So, but at the same time, this current increases. So this current decreases. If this current decreases, then ICQ decreases. So rise in ICQ is compensated by the decrease in ICQ. This is one technique. Third technique is a very handy technique, compensation of bias by thermistors and sensistors. Thermistors are simple resistors whose resistance decreases with temperature, and sensistors are those resistors whose temperature increases with temperature, right? A very simple technique. A thermistor is connected here. How does it work? As temperature rises, ICQ, this current, tends to rise due to rise in ICBO, right? But since the resistance of this thermistor drops, this parallel combination resistance drops. If this parallel combination resistance drops, then the potential here drops. The drop in potential here, it drops the value of VBB. And if it drops the value of VBB, the current ICQ decreases. Thermistor, the possibility of increase in ICQ is compensated by the thermistor here. Next case, a thermistor is connected here. The same circuit, thermistor is connected here. Here also, supplies a current IT through the emitter resistance, directly through the emitter resistance. And it creates a potential drop GRE. Now, when ICQ rises, this collector current rises with temperature, the thermistor resistance, it drops. If thermistor resistance drops, it increases the current IT, and increase in current IT increases the potential drop across RE. If increases RE, then the this potential goes up. If this potential goes up, then obviously the base current will go down, because the base current is supplied by the potential VBB and the reverse potential going up. So so increase in IC will be compensated by decrease in the base current. Then we use a sensor here. No additional supply, etc. rated. If ICQ tries to rise with temperature, sensor resistance S also rises. Resistor's temperature rises with temperature. Right? If this resistance rises, then combined resistance of RE and S in parallel also rises. If this combined resistance rises, then the current multiplied by combined rise in resistance, it rises the potential here. If it rises the potential here, then obviously base current flowing in this line will drop. So if collector current tries to increase, they will be compensated by drop in the base current. This is a sensor here. Here, as temperature rises, the combined resistance of these two also rises. Right? Rises. Then, if these two rises, then potential VBB decreases. I think you understand that. This is a potential divider. So potential here depends upon the ratio of this R1 plus S and R2. If this resistance rises, then potential here will drop. So if the current IC collector current tends to rise due to temperature, then at the same time, potential here drops, which reduces the collector current. So these are the four possible combinations of sensors and thermistors to compensate for the bias instability. Hello, Paul. Achha, okay. Okay. So these are the four basic methods of uh, bias compensation by resistors and sensors. So this bias stability, or rather bias instability, and methods of compensation completes here. And in fact, one part of this module is complete here. And I think next we shall ready to go into actual analysis of transistor based amplifiers. Okay, that we shall discuss in our next lesson.